right, so let's look at the correlation formula. What we saw last section is this formula. We have covariance on the top of the fraction and the product of the standard deviations on at the bottom. This same formula can be reworked as, let's put covariance, term of the stock, term bonds equals, well, we're going to move this term over here to the left side of the formula. We're going to have a correlation between stocks and bonds multiplied by the standard deviation of stocks multiplied by standard deviation of bonds. Okay, so we have a product of three terms. Both formulas will show up at the CFA exam, so you have to actually know both of them. Are they really hard to remember? Well, no. Algebraically, just one is the variation of the other. They're pretty much the same thing. So that's that way we can go between correlation and covariance relatively easily. Depends on what you need. So why are we calculating the correlation? Well, I mentioned that it varies between -1 and 1, so that's actually fantastic usefulness, right? It's highly useful now because you know the correlation of 1, right? That this is perfectly correlated. It means that whenever one goes up, the other one always goes down, and vice versa. When a correlation of -1, right here, means that when one goes down, the other one always goes down. Sorry, goes up as well. They always move in the opposite directions. -1 means their movements are mirror images of each other. So correlation of 0, here we have this blob of points. It does not allow us to draw any conclusions about the one asset if we know what happens to the other one. Basically, they're not related. They aren't correlated with each other. You could even say they're independent. So you do not see a real pattern here. You cannot draw like line like this or like this. I mean, none of these lines would make any sense. Most likely, the only line you could actually draw if you're on regression for this blob of points would probably like a horizontal line, which doesn't tell us much. Okay. So the other cases of negative correlation and positive correlation, positive, negative, you can see that the blob of points from 0 becomes more and more sort of a narrow, more well-defined when the correlation goes to one of the extremes, either positive or negative. So the blob of points basically tells us there's no relation, but when the blob of points starts to take shape, like an ellipse or even a straight line, that tells us that when whatever happens to one of the asset, the other asset, we can predict what's going to happen to it. Like if one goes up and the correlation becomes more and more positive in this direction, the other one will tend to go up more and more frequently. Okay, and in the case of correlation of +1, the relationship is 1-to-1. Basically, whenever one goes up, the other one will go up as well. All right. So, what's the disadvantage of the correlation? Well, it is it's a linear measure. Meaning what? If you have nonlinear patterns, like for instance something like this, you can clearly see that there is a nonlinear pattern here. You can see that there's clearly a circle, but correlation for this particular blob of points, or like scatter plot, that's the term you saw in your business stats class, that blob of points, well, the relationship is certainly there, but it's not linear. And if you try to apply a linear measure of relation between the variables, like correlation, you'd find that the correlation is actually 0. So that kind of mitigates the usefulness of correlation. But in our course, or even outside, well, correlation is still extremely useful because nonlinear patterns are somewhat harder to come by. But yeah, you will see that in sort of more advanced or more complicated assets or more complicated combinations of assets. So in the real world, we're going to use historical data to estimate correlations and covariances. What we used so far is something called scenario analysis, when we had recession, mild recession, growth, boom, all of those scenarios. In the real world, of course, we can also forecast what's going to happen to the economy, to the market. But most of the time, we're going to use past history to forecast the future. When we use past history, we're going to use a different formula for the covariance, which will be the input for our correlation formula. And the formula is something that you have seen actually before in FIN340 and in other business stats class. So we're still going to have deviations of every sort of asset from its mean, but the mean is going to be just the average. We're not going to use the formula of the probability of every scenario multiplied by return in every scenario over S. If we're going to use that formula, well, that's actually a general variation of the formula that we apply here. And when we look at historical data, we assume that probability of occurrence of every day of data or every observation of data is the same. So that's why we can use sort of like this formula that you guys know. But this formula is a more general formula that we saw first in chapter 5 and we used in the previous slides when we calculated the covariance, variances, and expected returns. So what we're going to have then is a sigma. Cap sigma stands for summation sign. So that's sum over 9 n observations. We have 100 days. We're going to have 100 terms. We're going to have 100 months. We're going to have 100 terms, and so on. And then we're going to divide these products. The sum of the products by n minus 1, which is something that you probably know from your AP stats or for your business stats class. Okay, this is the term. Why? Because we are actually working with the sample data. So we need to adjust for an estimation bias when we estimated the means. But that's, of course, not going to be the question in the midterm. All right, so how are we going to use this in practice? Well, we're going to construct something called a correlation matrix. This is an example of correlation matrix from March 2014. We're going to have the same terms on the x-axis and the y-axis. So it's a tip. It's a ticker for TIPS bond fund. And as you can see, GLD, AG, EMB, USO. And for every particular cell here, well, that cell is going to be empty. Right? Because that's, well, the correlation of USO and USO is actually 1, because they're the same thing. So how one relates to the other? Well, it relates as 1 to 1. Correlation is 1. So it doesn't tell us much. In this particular correlation matrix, what you see is that the lower the number, which is pretty good for us because the lower the number, we can probably get some diversification benefits. The assets do not move always in the same direction all the time. So when something moves in a different direction, most of the time, that's going to be useful for us to see if we can get diversification benefits. So the green ones are good. As you can see, the correlation is pretty low, 0.1, 0.02. That's low correlation here as well. The lowest one is here. So let's see how we can create one of these matrices. We're gonna use portfoliovisualizer.com. So let's see. We're gonna use, let's see what we're gonna use. Let's put Tesla, APL, SPY. Tesla, Apple, and SPY is an ETF for S&P 500, which by now you should be quite well familiar with, because probably have that ETF in your portfolios. Then we're going to include what? We're going to include, I usually in this time, I'm asking students to give me different options on what to include. So, let's say probably, what about GLD for gold? I don't know if you guys would like to compare that to a commodity such as gold. Let's say AG for the Barclays Aggregate Bond Index. So it's bonds. And then let's see VNQ, which stands for an ETF. I think it's a Vanguard Real Estate ETF. So we're going to have real estate bonds, gold. Then we have SPY, which is S&P 500 ETF, and 2 stocks. So let's see what happens when we press on the view correlation. It's going to use the available period of data, and the Tesla is a relatively recent company, so we have only 9 years of data. So we're going to use only 9 years of data here. Correlation matrix then is, well, between, so kind of draw on the page. It's between this column and the cell. As you can see, correlation between Tesla and Tesla has nothing here because what? Because it's 1 and it doesn't give us any information. So let's see, correlation between Tesla and Apple so far, and it's a monthly correlation, has been about 0.08. So they seem to be somewhat, although both are considered to be tech firms, they seem to be quite uncorrelated with each other. Correlation between Tesla, let's go down the column, and SPY is 0.13. It's not high either. The correlation between Tesla and gold, 0.03, pretty much 0. Correlation is negative with 0.29 with bond ETF, and with the real estate ETF, it's also slightly negative. So it seems to me that Tesla is not highly correlated with pretty much anything. It's sort of on its own. And you could think about this as well. Tesla seems to be driven by sort of firm-specific factors. And you could say it's firm-specific risk. This returns for Tesla seem to be affected by something else. They're not highly correlated with tech firms like Apple, not correlated with the broad index on the market. And it seems, well, of course, they're not correlated with the real estate either. So let's take a look at Apple. Apple is much highly correlated with S&P 500, not correlated with gold, and the correlation is pretty much 0 with the bonds, but quite high with the real estate. So Apple seems to be, highly correlated with pretty much everything else, except bonds. So bonds, just skipping slightly ahead, seems to be highly correlated with gold. Well, I wouldn't say highly correlated, by 0.38 in this matrix. It seems to be relatively high, and highly correlated with the real estate. So it seems to me that the bonds and real estate and gold tend to go up together more often than not. Right? So that really tells us something. So if you want to add negative assets with negative correlation, you could probably look into Tesla. Or if you want to, if you hold the broad market, like if you are here, this particular row, well, if you hold the broad market index, if you're 100% in stocks, why not add some bonds? Because bonds seem to have relatively low correlation with market. So let's take a look at the returns. Analyzed returns for every one of these assets seem to be positive. It doesn't tell us much because, well, in some years you might be losing money, but on average you are kind of making money. Except gold is still positive, but it is very low. You can see that most of the time, I would probably guess it's been several years when the gold had a very sort of negative return, and you end up losing money. All right, so monthly standard deviation, which one's the riskiest, is Tesla. So it kind of hints at, but remember, daily and monthly and annualized standard deviation, they all pretty much derive one from the other. We can use any one of these. I could have used daily, could have monthly or annualized. In all those cases, you can see that Tesla's standard deviation is twice as high as that of Apple. Seems it's twice as risky on just standard deviation basis, just looking at the standard deviations. On the other hand, Tesla's return, annualized, so per year, it's only slightly higher than that of Apple. So you can probably say that looking at these two stocks by themselves, looking at probably at the Sharpe ratio that you saw in chapter 5, you could probably say that Apple has a higher Sharpe ratio. Just eyeballing it. Okay. All right, then we have rolling correlations. What are rolling correlations? It's basically we just don't have one number for correlations for the whole period. We have a window of correlations. You see it starts in 2013. Why? Because our initial window, I have to see how big is our window. 36 months right here. You can see 36 months, which is 36 months. So about 3 years. And our first observation for correlation to 2013, which is 3 years after the start of the period, in 2010. Right, right here. So it seems that we have, we just took 36 months of the data, calculate the correlations, and then this is going to be our point. What we did for the next point, for the August, we just moved our window of data 1 month forward. So for every point of these, we're going to use the previous 36 months of data. So that's going to be like a rolling window. Just pretty much like a rolling window. For every point of correlations here, we're going to use 36 previous months of data to calculate the correlations using the formula that we have seen in the previous slides. As you can see, the correlation between Tesla and Apple varies over time. Sometimes it's pretty high, well, relatively high, 0.2, and sometimes it's actually negative. Correlation between Tesla and this SPY, it's quite often also negative, but tends to be relatively higher than between Tesla and Apple. Let's take a look at Apple and SPY. You can see the correlation between Apple and SPY is always relatively high. Well, because Apple is a large company and it's part of the S&P 500 index. So it kind of makes sense. The correlation never dips below 0.28. So what does it tell us? It tells us an important thing. The correlations actually vary over time. And that is something that if you study for the CFA exam or you manage complicated portfolios of assets, that's going to be actually more and more important because you're going to have to forecast that correlation, estimate the correlation. Most likely you're going to have to take into account that the correlations change over time. All right, so let's see. That's so far. By the way, if we have a project in this particular course, some sort of trading game, I would probably recommend you build a correlation matrix using this tool. So you can put that either in your prospectus or in your report or in your presentation. Right. So then we have an advanced stochastic correlation estimator here. I usually don't cover that in class. I used to cover that in 2014, 2015. So that tells us that's basically another way to calculate something called stochastic correlations. Correlations that change over time. Let's just click on correlation analysis. I'm going to choose Gauge DCC. That's something I use in one of my papers. It's dynamic conditional correlations, and Gauge stands for quite a long term, actually a series of words that just sounds like gibberish, so it's called just Gauge DCC. So we are going to select different indices. Let's select CAC 40 for France. Let's select FTSE. It's just, it seems to me that we just add this pair. Okay. So what we have here is the correlation between FIN340, which is the index, stock index for the 40 largest companies in France, and then we have Budapest stock market index. And you can see the correlation sometimes changes over time, but it's relatively stable. So this is a very different way to calculate correlations, but you can see it also allows us to look at correlations changing over time. And that's important because if you look all the whole period, all the way back to 1999, you can see the correlations sometimes vary by a lot for this particular pairs of indices. So that's again something much more advanced. If you work for a bank and sort of do a risk management, risk analysis, or maybe if you're an actuary, eventually you might be looking at these sophisticated models to forecast correlation. Let's go back to PowerPoint.